first thing I want to mention is in kind of here in the module section. Where did we? No, it's definitely. I don't see it. Oh, there it is. I'm standing right on it. The worksheet solutions. So those are the solutions to those 4 problems I gave, were the ones where you had to like kind of substitute in with the different components, but it wasn't like straightforward. So those are the solutions to that one. Then here was the other worksheet we did the other day with the frequency period and forces and accelerations. Then I posted the solution to that one underneath it. And then down here, I posted 6 more practice problems with Newton's laws. And I think these are kind of more like what you would expect on an exam. So if you click on that, it opens a page where there's the blank worksheets and then the solution. So if you kind of want to look those over, you can. Don't forget, we do have our exam next Friday over 4, 5, and 6. And we'll talk a little bit more on Monday about the topics and that kind of stuff. But I just wanted you to remember that that is coming up next week. It's going to be the standard format, 15 multiple choice, 3 extended response. You'll get your equation sheet. So, does everyone, any questions about that? And I'll probably try to get another, some other like token point worksheets up there as well. I just need some time to make them up. All right. Then if there's no more questions about that, let's go to this. So we talked on Wednesday. Oh, it's dark up here because I didn't. We talked on Wednesday about circular motion. So we looked at like tension in strings. We looked at like car tires holding the car to the road, because we talked about motion where V is constant and there's always an inward force holding the object to that path, right? And then what happens if that inward force disappears? The object flew at a right angle, right? So like if my object was on a string and it was going this way, as it crossed your path this way, and we let the string go, the object continued flying that way. It didn't fly inwards, right? And that was why I did that demonstration, is to point that the string holds it to the circular path, but because the velocity is at a right angle, the object, when the force disappears, the object continues moving straight, right? Now today what we want to look at, and I'll try to demonstrate this. Today what we want to look at, I don't know if I'm going to do it right. I didn't do this right in the last lecture. All right. I don't know if it's because the string is twisted or something, but yeah, we'll blame it on that. So the idea is we want to do things in circles this way now, right? We want to do circles like this, and we want to look at the forces involved going in circles. And that's what happened last time, is the cup. When I went to stop it, the cup said, no, I have inertia. I'm going to keep going. But this is the idea, right? We want to go in circles. And we want to look at, why does the water not fall out of the cup? Right? Things like that. Why is it? And like I said, if you go too far, then it'll fly. But we want to look at the forces involved in circles today, up like this way. Right? We did it this way on Wednesday. Now we want to go this way today. Right? And this covers all kinds of things, even like laundry machines, right? Like your dryer. It works on that principle. Oh, am I on the wrong day? I am. Oh no. So we aren't going to talk. So I'm going to do that lecture again. Not gravity. There we go. At least it doesn't have to type in a password. There we go. So we want to talk about this stuff today. So we're just going to jump in, and we're going to do a problem involving a roller coaster. Because roller coasters go in circles, some of them. But even a teardrop is still partial. It still has a curvature to it, and you could solve a teardrop if you wanted to. That like the ones that aren't pure circles like this, but they have kind of more of a curve to them. All right, so let's look at this circle. So when you're in a roller coaster loop, we want to look at, they tell us we're gonna look at the top and the bottom. We're gonna kind of come in, go around, and then come back out. Now they tell us our hill is 60 meters high. They tell us the mass of the rider is 50 kilograms. And they tell us you're moving at 30 meters per second. Is everyone good with that? These are what they tell us. And that they want to ask us now is, what is the apparent weight? And when they ask for the apparent weight, what variable are they asking us to find? Remembering all the way back to chapter 5. The apparent weight is the normal force. That is how you experience your weight. So remember that the normal force, this is the apparent weight. This is how you feel your weight. Right, that's kind of how like you experience your weight. And we said that, remember we did the elevators, we talked about being in the elevator and the normal force changed, so you kind of felt heavier or lighter as the elevator accelerated up and down. Well, the same thing happens in circles, right? So if you've ever been on a roller coaster and gone through a loop, you know that how you feel different at different points in the loop. Some places you're lighter, some you're heavier, and that's because the normal force on you is changing. And that's what we're going to look at in this problem. Is everyone good with that? So when they ask us, what is our apparent weight? We're looking at n at the top, question mark, and n at the bottom, question mark. That's what we're looking for, top and bottom. Is everyone okay with that? Does that make sense? All right. Do you have a preferred one to start with, the top or the bottom? The top. All right. Let's look at the top. So one thing we have to mark, this is the center of our circle. All right, we always want to mark where our center is so we remember which way our forces are pointing. So what's a force we should put on our diagram? Wait, yeah, class participation. So what else can we put on? Friction? Up and down, we'll leave friction out. It's going to come up though, but not on this, because we're just going to look up and down. So technically, yes, there's friction like this way working on the cart, but we're not going to sum it into that right now. All right. How about another force? Normal, but which way does my normal force point? You want to put it up because we always put the normal force up. But what I want you to think about is if this is the roller coaster and here's you as the rider, the normal force is because of the seat on you. So it works here, but when you go upside down, the normal force from the seat is pointing down. You can't see it on the camera because of the way I held it. But when the coaster is going around, the normal force from the seat on you points down. All right? So the normal force points down as well. Now, as a side note reminder, we say anything that points away from the center, away, this is a nice mark. I'm not writing big enough, but if it's away from the center, it's negative, and if it's towards the center, it's positive. All right? So now we can sum our forces in the radial direction, and we have mv squared over r. Because all of our forces point towards the center of curvature. So we come in, we write n plus w is mv squared over r. This, it's plus. It's like a directional, plus, directional, minus. Yeah. So now we can solve for the normal force because the normal force is mv squared over r minus w. We're going to come back and talk about this in just a second. But first, let's come up with a number. So when we want to find our number, it's going to be n is equal to 50 times 30 squared. Now I don't put in 60, I have to put in what number? 30 because I need the radius, not the diameter. So we plug in 30, and then we have 50 times 9.8. So our normal force is the question. Hopefully everyone got 1010, because this is 1500 minus. Your normal force is 1010. Now I want to point something out. When we start looking at this equation, there's an interesting result. And we have to think back to the elevator. So if you remember the day we talked about the elevator, we said there was one last case, and we said that was when the cable snapped. And when the cable snapped, what did we say was the normal force? It was free fall, right? The n went to 0 because there's nothing supporting you. You're just falling now. So if n goes to 0, that's bad day on the roller coaster, right? So when we look here, we notice that we have this term has to be larger than w, right? If v is not the right number, this number is smaller than the weight, n is not bigger than 0. And that means that the track, something is wrong with the coaster, and hopefully one of two things will happen. The coaster would go up and not make it up and just roll back down, or it would go up there and then they would realize something's wrong, it would lock the car to the track, right? And then they would have to make mechanical repairs to get you out. But the idea would be is if this isn't larger than 0, you don't complete the loop because n isn't larger than 0. So what we can think about is there is a V min, or we call V critical, to complete the loop. We find that by setting n equal to 0 and solve for V. Right? So what we can do, just as a quick aside, we can find the V min for this loop. Because we can say right here that 0 plus our 55 or 50 times 9.8 is equal to 50 V min squared divided by 30. Now I want to point out something as well. We noticed something on Wednesday. The critical speed when you took a turn on a road, did that critical speed depend on the mass of the vehicle? No. The critical speed here does not depend on the mass of the car either. So we see that V is equal to, this V min is 30, which is the radius, times 9.8 square root. So notice again, critical speeds in circular motion don't depend on the mass. We're going to see that a couple more times today. And so what's our V min or V critical for this loop? What? 17.1. Okay. And so we see that if you're going less than 17.1, you won't clear the loop. So that is the minimum speed you have to go. Now, we also didn't include this, but there's other physics we would have to account for, like the fact that gravitational energy actually takes speed out of the cart as it goes up. So you would actually have to account for all these, there's some other factors we would have to account for to make this the correct problem. But for now, this is good. We're looking at different parts of the problem. All right, so the next part is what? The next part is looking at the bottom. So when we're coming through the bottom here, there you go, get a hat on. So the idea is that when we're coming through the bottom, what forces are acting on us? What? Weight is down. All right, anything else? Normal, and which way does that work? Up. Yeah, this is a normal looking problem. And our center of curvature is there. So this time here, we see that our plus direction is towards the center and our negative is away from the center, right? So when we go to sum our forces in the radial direction, we have mv squared over r. Is everyone okay with that? Then when we come in here, we have n minus w is equal to mv squared over r, or n is w plus mv squared over r. When you're going through the bottom of a loop, like a crest or a loop or something, you will always feel heavier. Whenever you come through a dip, you'll always feel heavier. Is everyone good with that? So in this case, it's 59.8 plus 50 times what? 30 squared over 30. And then our n is some number. Everyone okay with that? So we solved two different cases. We looked at going upside down, and we looked at coming through the bottom. Is everyone good? All right. So then let's change this up. And let's look at this. So how many people have ever seen this amusement park ride or been on it before? Cool. A few people. And this is the fun one where like you stand up against the wall and then they start spinning the thing. And you don't even kind of notice it spinning, but then once they start spinning it, then they drop the floor. And then you just stick to the wall and you don't fall. So I found this random video online of people doing this. Oh. Then it kicks me in. So these people are completely but I'm glad they posted this video. Then what you're going to see here is you'll see in a second that they drop the floor. Because you'll see these people sticking to the side of the wall. All right, so we've watched these random people. All right, so what we want to do is we're finally going to use learning catalytics. All right, so the question that I'm going to push is this one. What are the forces? I never stopped the session, so here we go. I'll deliver it again. You guys see this question on learning catalytics? Okay, good. So I want you to pick the correct force diagram for the person in the ride. I think so. Anyone else need more time to answer? Is there anyone else? I'll give you another second if you do. It's just hard for me to tell how many people answered because I left it open by accident from the other class. We'll assume if you all answered. So let's think about this for a second using our force catalog. Our list of forces. So here's the wall. Here's the person. So what's one of the forces that we know to draw on our force catalog? Weight, and weight works down. So what's another force that we need to put on the normal? But this is where it's tricky, right? Because if you've been on the ride, you get pushed, you feel like you're being pushed which way? Back, right? And this is what makes it difficult to decide where to put that normal force. Because I've been on it and it feels like I'm being pushed into the wall, right? Just like when you go through the bottom of the loop, which I just erased, you feel like you're being what? You feel heavier and it feels like you're being crushed into the seat. Does that make sense? Like what I just like those are what you feel, right? But what is our definition of the normal force? It's perpendicular from surface to. So what way does my normal force have to work? It has to work this way. And I need one more force. Otherwise, weight would be what? Weight would you just fall down. So what stops you from falling? Friction. And friction is a parallel force from surface to object. So when we look at our forces, the answer that we should pick is A, right? Based on applying our force principles. Now, what we're going to talk about next is the idea that even though you do feel this, you feel this. But that comes up from something. That comes because when you're going around this circle, we said that the sum of the forces in the radial direction is mv squared over r. This is really MAR. You're experiencing an acceleration. Whenever you experience an acceleration, how you identify forces gets thrown off. All right? And so we can't, we have to be careful, even though you feel this is how you feel the normal force, but the normal force really is pushing you inwards. Because if the wall disappeared, you would fly off like Bob did the other day, right? The wall is there to hold you to the circle. Without the wall, you'd fly off, tangent to the line at the point where the wall disappeared. You wouldn't fly inwards, right? Is everyone good with that? All right, so that force that you feel that's not there, that's called the centrifugal force. It's not real. It's just a force that you experience when you are in this frame that has an acceleration. You mislabel the forces. So instead of calling it the normal, you would label it here. It's just you mislabel the force. It's not an additional force acting on you. You've just mislabeled the normal force. So we don't put that red force on our force diagrams because it's not a correct force. These are called fictitious forces because they don't exist. So I'm just telling you, don't put them on. We never put these forces on because they're not real. It's a mislabeling of the forces because you're experiencing an acceleration. This actually goes back to the first law the first law really deals with identifying frames with no accelerations, and then you can correctly identify forces. But we don't deal with it because most of the time we don't solve problems in accelerating frames. That's not what we would do. But my other example of this is your car door. So when you're driving in the car and you go to make a turn, so when you go to turn, you feel like you're being pushed out that way. You feel like you're getting pulled the one way, but it's really like the door's pushing you in, even though you feel like you're being pushed outward when you turn. And it's because you want to continue moving in the straight line and the car is moving, right? So you're in the frame that is rotating, you feel the force the wrong way. And I always remember this because like when I was in the car with my siblings, they would pile us in the back seat, and then everyone would lean and crush the person into the door, right? So you never wanted to be that person by the door. But these are the idea. These forces come up because of this acceleration, and you don't want to put the mislabel on it. This is good. You don't put that. But we'll mention this in another second. Is everyone okay with that? So just know those are called centrifugal forces. They don't exist. So here's a video that hopefully will help explain this. All right, so this is exactly what he's talking about. This person and the olive are the same thing, right? The forces on them are no different. So what I want to do is I'm going to solve, so the next problem, all right. The next problem is what's going on with the olive, but we can ask the same thing about what's going on with this person. They're the same problem. So let's take a look at what's going on with them, and then we can answer a few strange questions along the way. Okay. So when you're riding around in the graviton or you're an olive in the glass, you're experiencing the same system, right? So we're going to put our center of curvature in the middle, and we're going to look at what's going on. So the first thing we can do is we'll sum our forces in the y to have MAY. And what are our two forces? Friction and weight. So Fs minus W is equal to, and what's our acceleration? If you're on that ride, what do you want the acceleration to be up and down? You want it to be 0, right? You don't want to fall off the wall. That's the goal, right? So you want that to be 0. So what you need is you need the static friction force to be equal to your weight. Is everyone good with that? But we remember that mu static times N is the friction force. Is everyone okay with that? Now, when we come over here, we're going to sum forces in the radial direction to get mv squared over r. And what's our one force in the radial direction? The normal. So N equals mv squared over r. So the normal force depends on the velocity, right? It's velocity dependent. So let's take a look. So when we have, this is our normal force that we can put here. So if we need friction to be a certain value, R is fixed for the ride. The mass of the riders vary. But we're going to see that the mass will drop out. Because if we go mu static, mv squared over r equals mg. So when you're looking at the ride, the goal is to spin the drum fast enough, spin this thing fast enough, the tube, such that you will get people to stick to the wall. That's the goal. So as long as you spin the ride fast enough, the people will stick to the wall. So we can cancel the mass, and our V minimum to spin the drum here to get people to stick is GR over mu static square root. And if you go back and look from Wednesday, I was gonna say last week, but Wednesday, when you were trying to turn your car, it was GR times mu S. Right? So the safe speeds and things always depend usually on RG and then some other property of the system. Right? So the radius is a property. So if you're an engineer, you're going to build a graviton, you just make sure that you know your radius, local gravity, and then what do? You basically make sure you build the wall material of your stuff, and you know what the coefficient of cotton, polyester blend is against the wall, because that's what most people wear. And then you post a little sign that says, hey, if people wear slick rain jackets or certain types of material, they can't come on the ride, because that would throw this off. So you can build the ride for a general population, but not for certain things, right? And then you know what speed to spin your drum at. And so usually what happens is the operator starts spinning up the drum. Once it hits this above the minimum speed, then they drop the floor, right? Because they already know the answer to how fast they have to spin it. Is everyone good with that? And that's the same for the olive. That's the minimum speed you have to put in the olive to get it to go. Now, this is also one other thing, that this is very useful, not useful, but it could be used. How about that? It's a hypothetical, but they've tried this before. So we said that when we're spinning, since I can do this, I only get to do this once. All right, so when you're spinning this, right, and we said that this is the person, let's say, on that outside track radius, right? And we said that when you're on the wall, you feel as though you're being what? Pinned back, right? Or if you're on the rim and you're the cup of water, and you're this person, you would feel as the cup feels as though it's being pushed into the plate, right? Does that make sense to everybody? So if you're the cup, you feel like you're being pushed into the plate when it's going around. So if you were a person and you're in outer space and you want to simulate gravity to make people feel more at home, what do you have to do? You have to spin your drum of radius R to make this so it's the same as the weight of the person, right? And then that would be the same as artificial gravity. So the idea would be here, not worrying about mu s, you'd have V squared over R equals G. You spin your drum fast enough so that this value is going to get you to G, so the people feel as though they're at 9.8. And that's how science fiction shows always try to simulate gravity, like on their space stations and things like that. They spin a drum. Now, NASA actually tried this with the Gemini program back like in the 60s. They did little tests to test artificial gravity. Then some other engineer actually did build a ship that he proposed the plans to NASA for a realistic ship to travel that had a small amount of artificial gravity for the astronauts. But NASA turned it down. But it was proposed. You've seen that ship because they actually put it, if you've ever seen the movie The Martian, that's the ship that guy designed for NASA. They put that into the movie, according to his plans. But this is a way to simulate gravity, right? Because you would feel this, and this would be your weight if you're on the outside edge of that loop spinning, right? So it's a way to make gravity. Is everyone okay with that? So then let's do one last problem, okay? I'll do it over here so I'll erase this. All right, so let's do one more problem. This is our fourth variation of this type of system. So the first one was we went upside down. The next one, we went through the dip. We went on the outside edge, and now we're gonna go over the hill. All right, so there's 4 ways we can look at these problems, set these up. So let's take a look at going over the hill. So here we are. We're gonna go over our hill. And they tell us the radius of our hill is 3 meters. Now, when you go over a hill, the radius is underneath. So there's the radius of 3 meters. They tell us that the hill has a speed, or the hill, no, the hill's not moving. You're moving over the hill at 10 meters per second. I guess it depends on how you view it. And they tell us this person has a mass of 55 kilograms. And what they want to know is, what is the apparent weight? So what are we trying to find? So we're looking for n. So let's set up our picture. So what forces do I need? Weight, and that's going to work down. What's another force that I should put on my diagram? Which way? Up. That's where your seat's pointing, which is well. Now we remember that we count anything towards the center as positive and away as negative. That's how we set up our system. So when we go to sum our forces, we sum our forces in the radial direction, we get mv squared over r. So we plug in. We have W minus N is mv squared over r. So then N is equal to W minus mv squared over r. Or in this case, N is 55 times 9.8 minus 55 is 10 squared, 3. You said 294? And what does that mean? If n is not bigger than 0, that means you are no longer in contact with the surface. That means you went airborne. So what would really have happened is probably somewhere back here, you would have lost contact with the hill and started flying over the hill like Dukes of Hazzard style, right? And you would have come over here and you would have landed down over here somewhere, right? So what that tells us is the following. Notice what we have here, W minus mv squared over r. We want this quantity to be positive to safely clear the hill. So we can think about finding a V critical again by setting n equal to 0 and solving for V. So what we do is we say 0 is equal to W minus mv squared over r. And we can now solve for the V that we can safely go over the hill, right? Because if we go too fast, we lose contact with the road, and then you can bottom out your car and crack the frame of your car or something. So what we notice is that mv squared over r is equal to W. But we know W is mg. So notice again, what keeps constantly canceling in circular motion with critical speeds? The mass. No critical speed would depend on the mass for almost any of these problems. So our V critical, again, is the square root of RG. It's a property of the system, right? So V critical is the square root of 3 times 9.8. So what's our critical speed?
5.4.
5.4. So if you want to maintain contact with the road, you go over the hill at 5.4. If you're faster than that, your car will go up in the air, right? And then you have to hope that you don't hit too hard when you touch back down, or you have really good shocks. Is everyone good with that? Now, one last side note, another side. If you've ever looked at a dryer, you've ever been to a laundromat and dried clothes, and you've watched the drum spin around, and then somewhere right about here, your clothes fall off the. If it's fascinating to go watch a dryer. But when you do that, the clothes fall down. They lose contact right here at that point. And it's really because when you're looking at this drum, every time we solved a problem, we solved at the very top and the very bottom. But that's because we removed all the forces at angles, so we didn't have to worry about sines and cosines. But you can solve the problem at an off point, using breaking forces into the components and everything. And what happens is the dryer is designed to spin at the right speed. So right at this point, this contact point, you lose the normal force and the clothes fall off the drum. And so what happens is the clothes tumble around, fall through the air, tumble around, fall through the air. And that way they dry faster, right? And then the holes are also designed to help throw the water off, pull water off the clothes as well. All right, to keep the hot air moving and pull water off. But this is the idea, is they fall through that, they just follow this. Hey, I spin this at the right speed, and then normal force vanishes. And the clothes fall. In case you didn't know, I'm sorry. The guy who made that, very rich. But this is the idea of circular force, like looking at weight, how weight plays into circular. All right, so we have force cases that we'll look at. Okay. All right, that's all I have to say. I will see you hopefully on Monday.
Right.